Laplace transform of the following function. So we have f of t is equal to e to the negative at times sine omega t. So when they say determine analytically, they mean do it using brute force. So plug it into the equation for the Laplace transform and solve it. So recall the equation for the Laplace transform is the integral from 0 to infinity of e to the negative st times f of t dt. So what we'll do is we'll just plug that in, but first we'll go over, first we'll transfer sine into exponential form. So recall that sine omega t is equal to e to the omega I t minus e to the negative omega I t over 2I. So then that gives us, so when we plug that in, we get the integral from 0 to infinity of e to the negative st times e to the negative at times e to the omega I t minus e to the negative omega I t over 2I dt. So what we can do straight away is we can take the 1 over 2I out. And so the key thing to remember is you always want to have the negative in front of the coefficient of t. So that that way it's a lot easier to manipulate when you plug in infinity after you integrate. So what we're going to have in that case, so by expansion we get e to the negative, then s plus a minus omega I t minus e to the negative s plus a plus omega I t dt. And so now we can just evaluate these integrals on, we can just evaluate the integral straight away. So that gives us 1/2 times negative 1 over s plus a minus omega I plus 1 over s plus a plus omega I, and this has an exponential with some stuff up top, but it's not that important, so I'm not going to rewrite it at the moment. So it's plus, and then that is between 0 and infinity. So when we plug in infinity, So when we plug in infinity, because it's a negative exponential, it'll automatically go straight to 0, and then when we plug in 0, it becomes 1. So the exponentials therefore are eliminated. So this leaves us with 1 over 2I times negative 1 over s plus a minus omega I plus 1 over s plus a plus omega I. Yeah. And so now what we're going to do is we are going to combine the fraction so that we can get a common denominator. So the way that we do that is we multiply each one by the other fraction's denominator. So then that gives us this expression. So if you look, the s and a's for the top are going to cancel out, and then that'll leave us with negative 2 omega I as the numerator, and then on the bottom, if we view the s plus a as a single term, then when we expand the bottom, it's just going to result in a difference of squares, which with the i's is just going to end up being an addition of squares. So we get 1 over 2I times negative 2 omega I over s plus a squared plus omega squared, and now we just cancel the I and the 2, leaving us with negative omega over s plus a solve differential equations, pardon me, we're going to actually solve differential equations using the Laplace transforms. So for this, we're not going to do the brute force method of plugging it into the equation. We're just going to go ahead and use identities that we already know, and if you don't know them through practice, you'll just learn what they are, and they'll just, the more you practice, the more concrete it'll be. Kind of like identities such as sine of pi over 2, that is 1, etc. Similar to that. Alright, so the first one that we'll deal with is we have second derivative of x with respect to t plus 2 times the derivative of x with respect to t plus x is equal to 1. And then we have, for initial conditions, x of 0 is equal to x prime of 0 is equal to 0, which simplifies a lot of our problems. So what we do is we'll start off by breaking this up into different parts. So we'll overall take the Laplace transform of the whole thing. But the Laplace transform, as you know from the definition, is an integral, so you can break it up through addition. So what we can do is we can actually take the Laplace transform of the second derivative of x, which I'm just going to write as x prime, x double prime, correction. And then the, and 2 is a constant, so it can come out. Okay, so now for the second derivative, it is s squared, and I'll just denote it capital X for the Laplace transform of x, minus s x prime of 0 minus x of 0. No, sorry, prime goes in. And so for the single derivative, it's s times x minus x of 0. And then for x, it's just x. And this is 1 over s. So, as we can see here, any of the initial conditions go straight to 0. So this results in s squared x 2s. As remember that we still have the 2 here, so we'll just write it there just for clarification, and then x and 1 over s. So now we're going to recombine our differential equation through addition. So we get s squared x plus 2s x plus x is equal to 1 over s. So now a common factor for the left-hand side is the Laplace transform of our function x. So when we factor it out, we get s squared plus 2s plus 1 times x is equal to 1 over s. Now, we can factor this straight away if we want, but it's not necessary to do it at this stage. So what we're going to do is we're going to isolate for x. So we get 1 over s times s plus 1 squared, which is just this function factor.